Hello, and welcome to this presentation, Understanding Phasor Diagrams. In this presentation, we'll provide a short technical introduction to phasor or vector diagrams and how they're used in measuring, analyzing, and troubleshooting three-phase power applications. This presentation assumes a very basic knowledge of three-phase power and related concepts. If you're not familiar with three-phase power, or if you'd like a brief review, you might want to watch the presentation Understanding Three-Phase Power Fundamentals before beginning this presentation. As you should already know, a three-phase power system has three phases, each with its own voltage and current. One way of analyzing these is plotting voltage and/or current versus time on an oscilloscope. For example, this is what the three voltage phases would look like in a so-called balanced system. But in many cases, it can also be helpful to view a snapshot of the three phases simultaneously. That is, the magnitude and relative phases of voltage and current at a point in time. The result is what's commonly called a phasor diagram or vector diagram. In the remainder of this presentation, we'll provide a brief overview of phasor diagrams, as well as how to use and interpret them. As mentioned a few moments ago, a phasor diagram is an instantaneous view showing the relative magnitudes and phases for both voltage and current. The length of each of these phasors shows the magnitude in volts or amperes, and these are normally RMS values. In almost all cases, the phasors are labeled to show which phase they represent. There are numerous different ways of drawing the arrows in order to distinguish between voltage and current. One common convention is using an open arrowhead for voltage and a closed or solid arrowhead for current, as shown here. Other methods include solid lines for voltage and dashed lines for current, or using thicker lines for voltage and thinner lines for current. And since voltage and current may change during measurements, diagrams can typically be scaled both manually and automatically. Phasor or vector diagrams are commonly supported on most test and measurement instruments used for making power measurements. These include oscilloscopes, as well as dedicated power analyzers. Note that for a three-phase measurement, 6 measurement channels are normally required, 3 for measuring voltage and 3 for measuring current. Test and measurement instruments that support phasor diagrams also usually provide numerical values for voltage and current, as well as the value for the system frequency. The most common application of phasor diagrams is verifying the measurement setup is correct and that plausible values are being measured. For a balanced three-phase system, this starts with all three phasors being displayed. The voltage phasors should be separated by approximately 120 degrees and have roughly equal magnitudes. And the same is also true for the current phasors. Another quick check is that in a balanced system with an inductive load, the current will usually lag the voltage in each phase by tens of degrees. But note that this lag should never be more than 90 degrees. One other way to use a phasor diagram is to check that the phases are in the proper order or sequence. The phasors for each phase all rotate at the system frequency. This is most often 50 or 60 Hz. By convention, this rotation is shown counterclockwise. In this animation, we're looking at only the voltage phasors, and we can see how the angles of each of these phasors changes over time, and thus why the phasor diagram would rotate counterclockwise over time. In order to have a relatively stable or stationary diagram, one phasor, usually the voltage phasor of the first or A phase, is chosen as the phase reference, and this phasor will then be used as the 0-degree point for all phase offsets shown in the phasor diagram. Most often the reference phase is shown in the 3 o'clock position on the phasor diagram. On some instruments, you may, however, see the reference phase in the 12 o'clock position. Since all other phase angles are calculated from this reference phase, the voltage phasor used as the reference should always remain in this reference position. Now that we've covered the basics, let's look at a couple of examples of using phasor diagrams to diagnose incorrect connection wiring. In the example on the left, the current clamp or sensor on the C phase has been connected backwards, since the current phasor is pointing 180 degrees opposite of the general area where we would expect it to be. The example on the right shows a situation in which one phase is missing entirely from the diagram. This could be due to incorrect cabling, but may also be caused by incorrect configuration of the measuring instrument. Next, let's return to the balanced three-phase example we showed earlier in this presentation. Recall that a three-phase system is balanced when the voltage phasors have the same magnitude and are spaced 120 degrees apart, and when the current phasors have the same magnitude and are all spaced 120 degrees apart. And remember that for an inductive load, such as a motor, the current phasors will lag the associated voltage phasors as shown here. The smaller the angle between a pair of voltage and current phasors, the more resistive the load is, and thus the higher the power factor. When load conditions change, the magnitudes of the phasors, particularly the current phasors, may change as well, although the angle between the phasors should remain constant if the nature or impedance of the load also remains constant. Unlike the previous diagram, this phasor diagram shows an abnormal situation. Although we still see the same 120 degree separation between phasors, and although the voltage magnitudes are still similar, there's an imbalance in the current between the phases. Namely, the magnitude of the current in the C phase is significantly greater than the magnitude of the currents in the A and B phases. This kind of current imbalance is undesirable and can lead to numerous issues or problems, such as overheating or a loss of torque in motor applications. The ability to quickly and visually diagnose these kinds of imbalances is one of the main advantages of using phasor diagrams. Let's end with a brief summary. Phasor or vector diagrams are used to quickly visualize the magnitudes and relative phases of voltage and current in multi-phase applications, and these diagrams are most often produced by oscilloscopes or dedicated power analyzers. Since the voltages and currents in each phase are constantly rotating, one phasor, typically the phase A voltage phasor, is chosen to be the phase reference, and all other phases are plotted relative to this reference. There are two main applications of phasor diagrams. The first is diagnosing issues with the test setup or connections, such as a missing sensor or a sensor that's connected backwards. The other application is making a quick visual check as to whether the phases are balanced, that is, whether the phases are properly offset from each other, and whether the phasors, particularly the current phasors, have similar magnitudes. This concludes our presentation, Understanding Phasor Diagrams. If you'd like to learn more about power measurement, power analysis, or power measurement solutions from Rohde and Schwarz, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.